Thank you, Jim. I'm here today representing a team of retired NASA scientists and engineers who have been looking at this human-caused global warming controversy intently for the last 3 years. And I'm also here as a representative of my local Catholic parish in Friendswood, Texas, where many of my friends and parishioners are praying that Pope Francis will have discernment as he looks into this global warming controversy. Our team is a volunteer group, primarily retired NASA engineers and scientists, but we have others. The core group of NASA retirees is more than 20, and we have about 37 members in our entire research team. We started in February of 2012. Our initial goal is to determine the extent to which burning fossil fuels can cause harmful global warming. And I'm going to tell you the bottom line of our research. We're going to run out of fossil fuels on this planet before atmospheric carbon dioxide levels can rise to a level that would cause harmful warming. That's the bottom line, and we've done a very thorough investigation. We aren't climate scientists, but we do have the same education, training, experience in the same scientific disciplines that climate scientists use. We're working as a team of specialists, as we've always worked at NASA, and we cover the whole spectrum here. But we bring something to this controversy that many climate scientists do not. I don't think any climate scientists have the kind of expertise that we've had in more than 50 years of the manned space program of identifying and mitigating threats. We know about threats, and we know how to prioritize them and deal with them to save human lives in space. And so that's what we've been doing, exploring the unknowns of manned spaceflight for more than 50 years. We define problems in terms of a deviation from normal. And we have a lot of details as we go in to find root cause of a problem. The fact is that global temperatures are not deviating from the normal limits of the last 10,000 years. The last 10,000 years have been a very stable time in the history of the planet. We have, in our study, bounded the warming that could possibly occur from burning all the fossil fuels on the planet, and we concluded we don't have a serious nor an immediate threat requiring global action. In a space situation where you have limited time to solve a problem, you have to prioritize the threats. I think hunger on the planet is a much more pressing, serious problem than climate change. And we know for certain that putting carbon dioxide in the atmosphere helps with plant growth, helps tremendously. The UN is very uncertain about climate change. And I'll talk about that uncertainty here in a moment. So our conclusions from our study are that due to worldwide rising energy demand and rising fossil fuel prices, as these fossil fuels are consumed, you're going to have a market-driven transition to alternative fuels. And that will occur before any problems with the climate can occur. In the U.S., we need a national energy plan to ensure our energy future, because so much of our imported oil comes from unstable places around the planet, and they threaten our supply. We have enough energy in the United States to be self-sufficient, but we are not self-sufficient at the present time. I got into the climate concern because I wanted a national energy plan for America, and this climate hoax was standing in the way of progress. And once we get this climate thing set aside, I hope that we can work on ensuring our energy future. The climate alarmism results from complex climate simulation models, not from data. And I'm a modeler. Thanks. In another discussion, my early job at NASA was writing computer simulations, developing computer simulations to understand whether the lunar lander would turn over or not when we landed on the moon. It was a phenomenon that we couldn't really do good experiments with on Earth, and we needed a computer simulation. But we made sure that computer simulation could adequately model what would happen with scale models dropped on the Earth. These climate models have never been shown to agree with any physical data. And you've seen some of that already. I have a few charts on it. So the models are not sufficiently accurate to guide public policy decisions. At NASA, we did not make decisions for design or operation with an unvalidated model. And that is the biggest mistake that climate scientists are making today. This is just another way of showing that the models, these are the latest models the United Nations has studied and published, they don't agree with the data. But yet most of the conclusions that the IPCC reaches are on the basis of these models, which to me is just silly. Let's talk a little bit about how climate sensitivity to carbon dioxide is defined. These are definitions that the United Nations uses. Equilibrium climate sensitivity. This is loosely defined as the global average temperature rise that will eventually result from doubling CO2 level in the atmosphere. It's computed by these complex, unvalidated computer models, but they predict what happens after 1,000 years from now. These are the same kind of models that you do 10-day weather forecasts with. And they're taking these models and running them for 1,000 years where, in my view, the answers are pure garbage. So this is the mainstream climate. This is where the consensus and 97% of all climate scientists agree that equilibrium climate sensitivity is as low as 1.5 degrees C and as high as 4.5 degrees C. This is a factor of 3 uncertainty in what's going to happen. These people have been studying this issue for 35 years. They spent billions of dollars studying this issue, and they haven't changed their uncertainty range at all. Now, in my book, you're not doing your job if you study this thing for 35 years and haven't made any experience. We put men on the moon and got them back safely within 10 years. So if we were working this problem, the first thing we'd do is get rid of the uncertainty. But the United Nations does not get rid of the uncertainty because they know that data supports the low end of their uncertainty range and their invalidated models support the high end. They keep the model results in and give it equal footing with the data, as we've seen with other speakers. If your model doesn't agree with the data, throw it away. It's going to mislead you. And my view is, if they've been studying this for 35 years, was reduction of the uncertainty range ever the goal of the research? What is the goal of the United Nations research? They're not getting ahead in this game. They also have a measure called transient climate response. And this is something that would happen over, say, a century or two if you double CO2 in the atmosphere. You don't have to wait for 1,000 years to see the full effect. And they define that as the warming you could get by doubling CO2 in the atmosphere at a rate of increase of 1% per year. That's more realistic than their equilibrium climate sensitivity, but it's still hypothetical. The actual rate of increase of CO2 in the atmosphere is about half that rate. So immediately when we looked at what the United Nations was doing, we don't like their definitions. There's no way to check them. You can't check them 1,000 years from now, and you can't check them at a 1% per year because that's not what the atmosphere is doing. We wanted a definition that says we can check this climate sensitivity with actual data. So our team defined something we call transient climate sensitivity. It's very close to TCR, but we're saying that transient climate sensitivity is the rise in the global average surface temperature that you would get by the gradual rise of CO2 in our atmosphere until it doubles the way it's actually happening. A variable rate and a small rate. So TCS is a verifiable quantity using actual data. You cannot verify the IPCC definition with actual data. And we determined what this TCS value is because we've already had a 40% rise in CO2 in the atmosphere since 1850, and we've had about 0.8 of a degree Kelvin, which is 0.8 degrees centigrade. We determined conservatively that TCS is 1.2 degrees. If you double CO2 the way we're doing it, very slowly, at the time you double CO2, you'll get at most 1.2 degrees of warming, and that's not alarming. Additional 1.2 degrees of global warming is more likely to be beneficial than harmful, especially when you see the beneficial effects of more CO2 in the atmosphere. Now, I want to put things in perspective. I'm sorry, I didn't start my timer.
All right.
Okay. What we really need to be worried about is the bottom of this chart that you may not be able to see. But we are dangerously close to the level of carbon dioxide in the atmosphere that it takes to grow plants. If the carbon dioxide level drops below 150 parts per million, all the plants on the planet die. We're talking about doubling CO2 from about 280 parts per million to 560 parts per million, sometimes, I think, later this century. But where we are is way down here at the bottom, just above the level that we need CO2 to grow plants. On the space station, where people are staying for a year or more, we allow 5,000 parts per million. That's more than 10 times the level of CO2 we have in the atmosphere today. On a U.S. Navy submarine, we allow 8,000 parts per million, and the industrial codes in the United States allow more than 10,000 parts per million for limited exposure. Now that's the reality of where we are. We're talking about doubling something from a very small level that is not going to be a problem. This is how CO2 has actually evolved in our atmosphere since about 1750. We've been taking good data since about 1959. That's the blue part of this curve. The earlier part was determined from ice core data in Antarctica. And our projection for CO2 going forward is this red dashed line. So all of this is a projection. We're going to double this level from here in about 2060, 2080. And this gets to the double level. And we predict by 2100, we would have 585 parts per million in the atmosphere. The United Nations predicts, doesn't give a justification for it. They predict 936 parts per million. We think that's more than you'll ever get from burning all the fossil fuels on the planet. And this is all they put out in their last report of what's going to happen if we don't start to control CO2 emissions. We've checked our numbers. We used the ExxonMobil 25-year forecast for energy, and the CO2 we computed came exactly on our projections, so I'm feeling pretty good about it. Okay, this is my simple climate model. I've been a modeler for more than 50 years, very complex models. Nothing as complicated as a climate model. But I've always had some kind of simple model to make sure that my big computer program was giving good results. This is the simple climate model of the Earth's surface. We have the sunlight coming in. That's the amount of energy per day, 341.3 watts per meter squared. I don't guarantee you these decimal points. This is mainstream climate science numbers, okay? I'm using their data. Some of that is reflected from clouds, the atmosphere, and the Earth's surface. A is the albedo of the Earth, which is like the reflectivity of the Earth. And this is what mainstream climate science says is rejected, roughly a third of it. Another part of the energy goes into the deep oceans of the Earth, very small amount. And the rest of it has to be radiated from the surface through the atmosphere, which is a very complex process. This we have a law of physics, the Boltzmann law for radiative heat transfer. So the heat of the planet has to obey this model. Can you read this equation? Okay. The emissivity of the surface is affected by greenhouse gases in the atmosphere, and we tried to indicate that by saying E, emissivity, is a function of water vapor, carbon C, and other greenhouse gases, G, and it's equal to the reflected energy minus that goes into the surface. I'm going to use a little calculus here that I don't expect everyone to follow, but I want to show you how we started with this simple model that is the big picture, and it didn't come through. But anyway, if we take a differential of this equation, we find out how the changes in some variables are affected by changes in other variables. And so we get down to where the change in temperature is a constant, 0.302, times the changes in emissivity due to the greenhouse gases, plus these other terms, 1 minus the albedo times the change in the sunlight coming in. The sunlight times the change in albedo, and any change in the heat going into the deep oceans. The climate scientists call these changes, these terms, they call that radiative forcing, and they have certain values for it, and they have certain values of radiative forcing for CO2 in the atmosphere. This is the data. This is the Hadley Climate Research Unit data from the UK. It does show an increase in temperature since 1850, but it also shows some wiggles of the data. The important thing to remember is all of these greenhouse gases changes, they are asymptotically increasing. Okay, there's no way an asymptotically increasing greenhouse gas can cause wiggles in the temperature data, because this equation comes from the conservation of energy. All the wiggles are going to be associated with these terms over here, which involve the heat that's going into the deep ocean. And this was the temperature variation going on before 1850. This is a reconstruction of northern hemisphere temperatures from paleoclimate. We had large swings in temperature, 0.8 of a degree, before, and all of this happened while CO2 was constant. So we took this into account. And using this, we came up with an equation that we should fit the data, and we're going to find out some unknown values in this equation that fit the data. This is the greenhouse gas part. This is the sunlight increase over time, which is very small. And these cyclic terms, this is a long year climate cycle that models the 2,000 years before us. And this is a 62-year cycle that's really, let me go back. This 62 years, we could just see it in the data, so okay, we got to take that out because that isn't CO2. So this is how these equations fit this data, and they do a good fit. And the wiggle is a 62-year cycle that scientists are starting to understand. This is what we call the pause. This is the temperature that hasn't changed in 16 to 18 years. And we predicted that with these curves. We predict it's going to go on for another 20 years. And then because of this natural cycle, it's going to rapidly increase and then flatten out again before the end of the century. So this is describing, we have a theory, it does describe the data, and we're confident that we're not going to have a problem. We're saying 1 more degree centigrade at most. We've looked at it with different assumptions about the longer term climate cycle. And here's, we've done our most conservative fit. This is where we get at most 1.2 degrees of warming for doubling CO2. And this just shows, at this point, in the middle of the next century, we're going to have burned all the CO2, burned all the fossil fuels on the planet, and the most you can increase is another 1.2 degrees, which is not going to be harmful. This is how our research compares to others. We're at the bottom, and all the new research is coming down to lower climate sensitivity. None of this is in the latest IPCC report. Our conclusions, our climate models are not sufficiently accurate for use in critical public policy decision making. The AGW, anthropogenic global warming, can be bounded using available data. We should expect a modest amount of warming. That warming is more likely to be beneficial than harmful, especially with more CO2 in the atmosphere. The United Nations recommendation for worldwide CO2 emission controls is not supported by physical data. Thank you.
Thank you. Any questions? Any questions for Hal?
Hi, Kyla. I have some quick question because you're working in Kelvin, right?
I need to
Sorry.
get closer.
Because you're saying it's a 1.2 degree increase at the most, but that's in Kelvin, so what would it be in Celsius? Same?
Kelvin and Celsius are the same thing. Kelvin's usually for absolute temperature, but climate modelers, climate scientists use K instead of Celsius.
The equations don't work in Celsius. You have to use Kelvin.
It's a text.
We're not talking Celsius to K, it's the two identical.
Kelvin starts at 0, whereas Celsius starts at minus
273.5.
No, so I was just trying to.
every increment is the same.
There was a question in the back.
Yes.
Yes, Chris.
Yes, I was just fascinated, because this is the first time I've seen your model. And we published the results of our own in reducing the simple model, which in some respects is the same as yours, in some respects different. But our conclusions were bang on the button, the same as yours. We think that a doubling of CO2 concentration should occur would give a warming of 0.8 to 1.3 Kelvin. I think your maximum is 1.2, so we're in the same ballpark there. And our best estimate is around 1 Kelvin, exactly the same as yours. And we also looked at the transient sensitivity at the end of the century and concluded that that would be 0.9, which again is very much the same ballpark as yours. And we've both done this with our team heat detector without having to compare tests.
But we're both using simple models based on conservation of energy that you put data into the terms of the model. Also, Judy Curry and Nick Lewis got the same answers we did, and they've lowered their number from 1.3 to 1.2 because the latest paper says the cooling of aerosols is not as great as the IPCC says it is. So I haven't published my work. You have. I'm not used to publishing work. It's out there.
To let me have a draft paper. I'll very happily build a draft.
Yes. Well, I have drafted the paper.
And then what I'll do is show it with the Chinese Science Bulletin, would be fascinating to have.
The paper our team has written, the paper we wrote is longer than what a journal would publish, but it is a tutorial.
Yes.
And we're trying to cut through all of the jargon of the IPCC and all of the smoke screen they put out and give a simple tutorial presentation based on this that I think most technically trained people could understand.
Well, I think that we would be able to put that into a paper around 6,000 words length, it's a typical standard academic paper. And if you would be interested, I'm very happy to work.
Oh, I would love to work with you.
On that. And then we have a good relationship now with the science authority, which is very good at the Chinese Academy of Sciences.
And I've read your paper. I like your control system approach to it because I do a lot of controls work. But I appreciate the offer. And I will take you up on that. It's just that we're continents apart.
Yes,
Any other questions?
Just a small question. You mentioned that the amount of CO2 allowed on a submarine is 8,000 parts per million. What's the point of making that?
I'm making the point that in terms of hazards for humans, breathing levels
Yeah.
are far removed from the levels we have in the atmosphere today.
Yeah.
The only hypothetical problem between the levels we have today and say 5,000 parts per million
Yeah.
is a proposed climate problem. But the United Nations is very uncertain about their concern.
But you're not aware of anyone saying that there is a serious danger from direct poisoning of human beings from the levels of CO2 in the atmosphere?
There is a problem. Once you get above 10,000 parts per
Yeah,
million,
but nobody's saying that
there's nothing harmful to humans
direct breathing.
below 1,000. We're never going to get above 1,000 by burning fossil fuel. We had 7,000 parts per million on this planet more than 400 million years ago. The natural process is 7,000 parts per million.
And if you go back to the
The geologists know all this stuff.
30% of the atmosphere.
But then once plants appeared on land, they began to take that CO2 out of the atmosphere. And we got dangerously close to not enough CO2 to grow plants during the last glaciation period. We're gradually coming back from this dangerously low CO2 level.
But you're aware that nobody's saying that breathing in a certain amount of CO2.
You're breathing 10,000 parts per million on me right now.
Yeah.
It's not
nobody-
hard.
Nobody's saying that's the issue. The issue is unrelated to that entirely.
I'm not sure.
Yeah.
I'm just showing you in perspective
Yeah.
where we are today, what all the controversies about, what we typically breathe out. This room probably has more than 1,000 parts per million CO2,
Yeah.
right?
But there's no concern on a submarine of the sunlight reaching the submarine and warming the atmosphere and that having an impact on the ability to grow crops.
I'm just saying that we're used to high levels of CO2 to breathe, and it's not a problem.
Yeah.
The only problem postulated is a climate problem,
Yeah.
which isn't going to happen.
Okay. Thank you.